Hello, welcome to the course UEC 001. In this module, we discuss some basics which will be required in this course. So let's start this module with energy sources. Energy sources. So in general, energy sources are of two types. It can be either independent or dependent, or dependent. And in both the cases, in this course, we will discuss about voltage source or current source. Voltage source or current source. So let's discuss first the independent source and let's begin with the voltage source. So these are further divided into two categories, ideal and practical voltage source. So let's discuss on ideal voltage source. So the representation of ideal voltage source is like this. Suppose this is a source and current flowing through the source is Is. Suppose I am representing the notation Vs and Is. So this voltage source is independent of this current and it do not have any resistance. Okay, so it is independent to the current Is, and over here I have shown that it is independent to the time. Okay, so it is not necessary that it is always independent to time. There may be a chance that some voltage sources are available. Those are depending on time also. So I'm drawing that representation current Is as a function of time. And in fact, this voltage will also be defined Vs as a function of time. And if you want to see their characteristics, relationship between voltage and current, so it can be defined like this. On this axis, I am defining Vs. Over here, I am defining the term Is. Then the value of this voltage is always fixed. The value of this voltage is always fixed and it will depends upon any level. So if I am defining V1, so it is fixed irrespective of any variation in the current. So this is the representation of my ideal voltage source. However, the practical voltage source is a bit different, and the representation of practical voltage source is it is a voltage source in series with a resistance. So this is the representation current Is, voltage source Vs, and if this is the resistance, one can draw the current and voltage relationship. If this is my Is and this is my Vs, earlier the reference voltage was this, the fixed voltage, but over here the effective voltage over here is less than this because this is my voltage VL. Then you can clearly see that voltage VL will be equals to Vs minus drop across this resistance, and this drop can be measured R multiplied by Is. So as the current increasing, this drop will be increasing. So effective voltage over here is a decreasing curve. So this is the VI relationship for a practical voltage source. Now similarly, we can study the current source also. So the current source, ideal current source will have a source current, suppose a value of is, or I am representing vs, or effectively vs of time. So both will be there. And if one is interested to find the value of voltage current relationship, if this is my is and this is my vs, then you can see that the value of current will also be fixed, suppose at some value of I1. So this is my equivalent current voltage relationship for ideal current source. And next, the practical current sources. So it has a current source and a parallel resistance. So likewise, the practical voltage source will have a series resistance, whereas the practical current source will have a parallel resistance. I'm saying that resistance R, this is my source current IS, and suppose the voltage at this terminal is, suppose at this node is my Vs, then, and I'm saying that this is my current IT, then the test current IT, this Vs I have mentioned over, so I can make over here also the relationship between voltage and current now. So you can check for any voltage of Vs when it is increasing. This was my earlier reference. Effective current, this IT, will be now a decreasing. This is my current Is, suppose current I1. And one can easily calculate this value current IT will be equals to the source current Is minus drop across here, and this can be measured by a simple voltage upon the current, so it is Vs divided by R. So this is the relationship of practical voltage source and practical current source. So these all are the independent cases. Now let's see the dependent energy sources. So giving you the I'm just briefing about that. The four possibilities are there. First is voltage controlled voltage source. In short, it is termed as VCVS. Next is voltage controlled current source, VCCS. Current controlled voltage source, CCVS. And the last is CCCS, current controlled current source. And the representation is like this. So these are the two standard representation: controlled voltage source and controlled current source. Now to solve the electrical circuit, two important laws will be used in this course, and these are Kirchhoff's law. So let us discuss first on Kirchhoff's voltage law. In short, it is termed as KVL, very popular. And according to this law, algebraic sum of all branch voltages in a closed path will be equals to 0. Okay, so let me read the statement. The algebraic sum of all branch voltages in a closed loop should be equals to 0. So idea will be clear with this circuit. So you can check. I have connected one external battery and say the value of battery is E. These three resistances R1, R2 and R3 are connected, and suppose a current I is flowing through this circuit. So you can check it's a closed loop. Okay, and with reference to this Kirchhoff law, okay, so the flow of current is always current will flow from positive terminal from higher potential to the lower potential. Therefore we have shown the clockwise direction over here. And with reference to this, suppose I am saying that the voltage across resistance is V1, this voltage is V2, and this voltage is V3. Then with this, what one can say that the algebraic summation over here. So the notation says that E minus V1 minus V2 minus V3 will be equals to 0, where V1, V2 and V3 are the voltage across resistance R1, cross R2 and R3 respectively. So one can write in this way: E equals IR1 plus IR2 plus IR3. So one can easily calculate the value of current using KVL. So this equals to E upon R1 plus R2 plus R3. So this KVL very important, and we will use later on in this course. Okay, so this is the basic of KVL. The algebraic summation of all branch voltages in a closed loop will be equals to 0. That means the energy supplied, all the summation of energy supplied will be equals to the energy consumed across the various components. Now let's see the second Kirchhoff's law, and it is Kirchhoff's current law. So according to Kirchhoff's current law, the algebraic summation of meeting of current to a particular node is 0, or we can define in this way: the summation of all incoming currents to a particular node will be equal to the summation of all outgoing current from that particular node. Okay, the sum of current entering to a node will be equal to the sum of current leaving to that node. So I'm considering that I'm having a node n, and suppose current entering to this nodes are current I1, I2 and I3. At the same time, these two currents are leaving the node, current I4 and current I5. So in general, one can define in this way also: summation of k varies from 1 to n, where n is the number of branches, will be equals to current Ik equals to 0. So if I am saying that the current entering to a node is positive and current leaving from the node is negative, then it can be defined like this: current I1 plus I2 plus I3 minus I4 minus I5 equals to 0, or ultimately current I1 plus I2 plus I3 will be equals to current I4 plus I5. So this is known as my Kirchhoff's current law. In short, it can be written as KCL, Kirchhoff's current law. Or let me see first voltage division, then on the basis of this we will find the voltage division rule. And for the simplicity, I am considering the same circuit which we have used in the KVL. So we have used three resistances over there. So I am using all the external supply. We have used over there the E using the same, and we have used the flow of current, that is my current I, resistance R1, resistance R2 and resistance R3. Likewise, if voltage across over here is V3, voltage across here is V2 and voltage across here is V1, then we have seen from KVL, from Kirchhoff's voltage law, from KVL, E will be equals to IR1 plus IR2 plus IR3, and we have calculated the value of I also, and it was E upon R1 plus R2 plus R3. If I am saying that R equivalent is my equivalent series resistance, then uh, the value of current I will be equals to E upon simple R equivalent. So in that case, if suppose I am interested to find this voltage V3, then from simple Ohm's law, current flowing through this resistance multiplied by the value of resistance. That means current I multiplied by resistance R3. So V3 will be, now I can easily put the value of current I. So it is E multiplied by R3 divided by R equivalent. In a similar fashion, let me write one more term. If I am interested to find the value of voltage V1, then the rule says that the overall voltage multiplied by the resistance of the branch to which you find the voltage. So I am interested to find V1, that means E multiplied by resistance R1 divided by equivalent resistance. So that is the basic. Now in order to understand in the form of rule, I am writing over here voltage division rule. This is very much important and mostly used. So for the simplicity, I am using two resistances only. Both are connected in series. External voltage V, R1, R2, current. And if I am interested to find the value of this V2 and V1 over here, then I can easily calculate from this rule, and rule says that voltage V1 equals to voltage across this resistance R1. So it is overall voltage across the series equivalent, that is voltage V multiplied by the resistance to which we want the voltage. So it is R1 divided by addition of all series resistances. So it is R1 plus R2. So this is known as my voltage division rule. Let me write explicitly the value of V2. So V overall voltage is V multiplied by resistance R2 across which we would like to find the voltage divided by R1 plus R2. As far as the proof concerned, we have seen on the previous session. Let me show you again. Easily calculate the value of current I. So it will be equals to V divided by resistance R1 plus R2. And for example, if you want to find the voltage V1, so it is current I into R1, simply put the value of I, so it is V into R1 divided by R1 plus R2, that is the proof. Now similarly, I am writing the current division rule. So likewise in current division rule, if my overall current is IS, two resistances have been connected in parallel configuration. Suppose resistance R1, resistance R2, I1 will be equals to the overall current IS multiplied by resistance of opposite branch, that is R2 divided by addition of two resistances R1 and R2. So let me write for current I2 also, overall current IS. I am interested to find this current, so multiplied by resistance of opposite branch R1 divided by R1 plus R2. Now you can check one thing. We know that in the parallel configuration, voltage is always same. So I'm saying the parallel equivalent of these two is so it is the basic term. First drawing the modified circuit. In this circuit, I will find the value of resistance R dash. I'm saying that this is R dash, and this R dash is nothing but the parallel combination of two resistances R1 and R2. and which we can easily calculate. So this was my IS, and you know that in parallel is still this Vs is same because we know that in parallel configuration voltage is always same. So now one can easily find this value, and this will be R1 into R2 divided by R1 plus R2. So let me see. If suppose we want to find the proof of this I1, okay, I am interested to find this current. So I have calculated the voltage. That means current flowing through resistance R1 is nothing but voltage divided by resistance of this. So I'm writing in this way, current I1 will be equals to Vs divided by the resistance R1. Now put the value of Vs. So from this relation, this is my value of R dash. Therefore, my value of Vs will be what? Is into R dash. And we will put the value of R dash and we will see the result. So over here, current I1 will be equals to my Is into R dash. Now for R dash, I am putting the value R1, R2 divided by R1. This is over here and R1 plus R2. So now I can check this R1 is cancelled out and I'm having a relation, and the relation is current I1 equals to Is into R2 divided by R1 plus R2. So now you can check this is the same which we have discussed earlier. So this is the proof, and if you want to see the proof of I2, so you can also apply the same method and you will get the answer. So this is another very important rule, the current division rule, and sometimes we will use this in current division rule in our course. Now let me discuss one more important aspect, and it is the source transformation. Source transformation. So this source transformation says that if we are having a practical current source or voltage source, then it can be converted to the equivalent voltage source or equivalent current source. So let me show you. Suppose I am having a practical voltage source. I am having practical voltage source of a series resistance R, voltage Vs, and suppose current from this is Is. So this is my practical voltage source. This can be converted to equivalent practical current source. That means a current source in parallel with a resistance. We have already seen how to find the practical current source. So this value should be my Vs, which will be equivalent to the voltage source. Now resistance will be same over here, and the value of this current source becomes this Is will be termed as the voltage source Vs divided by resistance R. So this is my practical current source. Okay, so over here, this is the source transformation from practical voltage to practical current source transformation. In a similar respect, we can see the transformation from practical current source to practical voltage source. So let's see that also. If I am having a practical current source, that is a current source in parallel with resistance. Suppose the value is Is, this is my resistance R, and voltage across this is Vs. So this can be converted to equivalent my practical voltage source, which will have a resistance in series with a voltage. So resistance value are same, and now value of this voltage source Vs becomes Is into R from Ohm's law. So this is conversion from current source to voltage source. So in this module, we have discussed about some basic aspects like what are the energy sources available which we can use in this course, voltage source and current source, We have seen the dependent and independent voltage and current source. Then we have seen the ideal and practical voltage and current source. Then we have discussed two most popular law that will be used in electrical circuits in this course, and these are Kirchhoff voltage law and Kirchhoff current law. We have seen how to apply these law in a network. Then we have seen the voltage division and current division rules, and finally the source transformation. Okay, so now stopping over here. Thank you.